Hey, welcome back to College Algebra. In this week's, we're going to talk about solving rational equations, roots, and rational exponents. We'll cover 5.5, 6.1, and 6.2 from our textbook. And then here's the measurable outcomes. Please look over these and make sure that you understand how to do some of these list of skill sets. Okay, 5.5, solving rational equations. Rational equation is simply an equation that involves one or more rational expression, which we covered last time. And so, for example, notice here we have a couple of rational equations, where again we have an equation that involves a rational expression, which is basically a polynomial over a polynomial. So 1 over x is a rational expression. 6w over w plus 1, for example, that's a rational expression, and so is this one. And so these are rational equations. So how do we solve a rational equation? So for example, here's a simple example. So one of the key component is to, because rational expression have fractions, one way to solve some of these equations to kind of clear the denominator. That way we can simplify the equation and then solve a much easier equation. So for example, in this example we have that the denominator is 1, 3, and 4. So we're going to find the LCD of all the terms, which is the least common denominator of all the terms. So 12 is a multiple of 2, 3, 4, and it's also the smallest multiple. So that's why it's the least common multiple, or the least common denominator. And so we're going to take that LCD, which is 12, and multiply the entire expression by 12. And so the reason why we do that is because we want to cancel out all of the denominator so that the denominator is clear. So if I do this, then I get that 12 times 1/2 x becomes 6x. We have to distribute the 12 into this as well. 12 times 1/3 is 4. 12 times 1/4 is 3, so we have 3x on the right side. And now notice that our equation has no more denominator, and now we can combine like terms. Bring the 3x over to get 6x minus 3x is 3x. Bring the 4 over here to get -4. X is -4 over 3. Okay, here's another one. This one's a little bit trickier because now we have 5x and 3, so we got to find the LCD of 5x and 3. And so notice none of these have anything in common, so we're going to take all 3 and just multiply all of them, so we get 15x. So 15x is the LCD of 5x and 3. And so we multiply everything by 15x. And so let's look at this expression by distributing this term. 15x times 3 over 5. Notice the 5 will cancel with the 15 to give a 3x. 3x times 3 is 9x. 15x times 1 of x. The x will cancel with the x to get 15 times 1, which is 15. And finally, the 3 will cancel with the 15 to give a 5. 5x times 2 is 10x. So again, choosing the LCD allows us to cancel each of these terms, right? Because 5x and 3 is part of 15x. All of them get canceled with a component of 15x, a factor of 15x. And once we do that, then the expression is easy to solve, and we get x is 15. Okay, here's another one. This one will be a little different than the previous one. Let's just see this. So again, we need to find the LCD. So this is the 1. Here's the denominator, w plus 1, w plus 1. So the LCD will be just w plus 1. So notice we have a restriction here, which is that w cannot be -1, because -1 will give you a division by 0 at the bottom. And so if I multiply everything by w plus 1 times 3, then w plus 1 times this, notice w plus 1 times this, the w plus 1 will cancel with this w plus 1. Again, that's kind of the point of the LCD, to cancel the denominator. And then w plus 1 times this side, again, that will cancel this as well. And so now we've got to simplify whatever's left. So distribute this. 3 times w, 3 times 1 is 3w plus 3. This will cancel and get minus 6w on the left side. And on the right side, these will cancel, you get 6. Combine like term, 3w minus 6w is -3w. Bring the 3 over, you get 3, w is -1. Now here's the problem though. W being -1, we have to be careful that we check that this is a real answer, because notice in the original expression there's a restriction on w. W cannot be -1 because -1 will cause a division by 0. And so in fact by following the process here, we only get one possible solution, that's -1, but -1 is actually not even a possible value because of the restriction that w cannot be -1. So really this equation that actually doesn't have any solution, because the only thing we can find is -1, but -1 is not even allowed to be plugged into the equation. So there's no solutions in this problem. Okay, what's the LCD for this one? Well, there's a 1 here, there's an x, there's an x squared, so x squared is a multiple of everything, and this is the smallest multiple, so we use that as the LCD. So multiply everything by x squared, so we have that x squared times 1 is x squared times this, again we have some cancellation, x times with x give you x, and then x times 3 is 3x, and then on this side the x squared cancels with x squared, so we have 28. Okay, so now we have, notice now for the first time we have a quadratic. In the previous example we have linear function, which is pretty easy, but this time we have a quadratic function after we cancel. And so how do we solve this? Well, we solve this just like we did in one of the previous section, where we try to factor and try to solve it that way. And so put everything on one side. So again, we have a quadratic, we want to put everything on one side. I put minus 28 on both sides so that we have this term. We will factor this. X plus 7, x minus 2. Again, this is learning how to factor a quadratic. We saw that in the previous lecture. And so x either could be a -7 or a 4. And notice that neither of these is part of the restriction of the original. The only restriction in the original is actually 0, because these are not 0, so both of these are solutions to our equation. Okay, 6.1. Let's talk about, now this is a new topic. Let's talk about the nth root. Okay, let's start with the square root. So b is the square root of a if b squared is equal to a. And so for example, let's find the square roots of these. So 5 is the square root of 25 because 5 squared is 25. -5 is also a square root of 25 because -5 squared is also 25. So 25 has two square roots, 5 and -5. In the same way, 49 has two square roots, 7 and -7, because both of them square will give you 49. And then for 0, 0 is the square root of 0 because 0 squared is 0, but it's the only square root of 0. And then finally, -9 has no square root because there exist no real numbers where once you square the answer give you -9, because -9 is negative. It doesn't have any square root, any real square root. Okay, so we notice that here's a pattern. The pattern is that if you have all real numbers, all positive real numbers, we have two real value square roots, one positive, one negative. 0 has only one square root, which is 0. And then a negative number will have no real value square roots. And because we have, for positive real numbers, we have multiple square roots, we're gonna, suppose a is positive, then this symbol, the square root of a, is gonna denote the positive square root of a. Again, because there's multiple square roots, in the case where a is positive, we're gonna let this symbol represent the positive square root. And we also call this the principal square root. And we put a negative in front of this symbol to denote the negative square root of 0. And then because the root of 0 is, it's negative square root of a, so principal root, positive, negative, if you want to take the -1 here. And then because 0 has only one square root of 0 is 0. Okay, so for example, what is square root of 36? Again, this is to denote the positive or the principal square root. So this answer is 6. Exactly 6. It's not -6, even though -6 is the square root of 36. This symbol denote the positive square root, which is only 6. In the same way, square root of the principal square root of 4/9 is 2/3. Again, we only look at the positive. This notation is only for positive. So 0.2 is a positive square root of 0.004. So this notation denote the positive square root. Okay, let's look at other examples. Notice that -144 doesn't have any square root. So in part A, there's no real square root. But notice in part B, there's a negative in front. That means that this denotes the negative square root of 144, and that is -12, because -12 squared is 144. Again, that negative in front means this is the negative square root. Or another way of thinking about this is that just to do the positive square root first, which is this expression, which is 12, and the negative is multiplied after to get the -12. Again, this is negative, so there's no square root of -0.01, and then taking the positive square root of 1 over 9 is 1 over 3. Multiply that by negative 1. Again, the negative is multiplied after. We get negative 1/3. Okay, what's the definition of an nth root? So now that we know what a square root is, what is an nth root? Well, an nth root is b is an nth root of a if b to the n is a. So for example, 2 is the square root of 4 because 2 squared is 4. 2 is the third root of 8 because 2 to the third power, or 2 cubed, is 8. 2 is the fourth root of 16 because 2 to the fourth power is 16. So this radical sign is used to denote the principal square root, as we saw. And the same way, this symbol, the radical with the n, called the index of the radical, denote the principal nth root of a number. And the number inside of the radical is called the radicand. And for example, by the way, instead of putting a 2 in front of it, we just simply do just the radical by itself. So without any index, it's understood to be a square root. But if I want a cube root, then you have to put a 3 in front of the radical symbol, and this is called the cube root. Okay, so here's some rules for finding the nth root. If n is bigger than 1 and is an even number, and a is positive, then the nth root of a is denote the principal or the positive nth root. So for example, the fourth root of 625 is the positive nth root, which is 5. But if n is positive, bigger than 1 and odd, then the nth root of a, this notation represents the nth root of a because there's only one nth root. But in the case where n is even, there will be 2 nth roots, and so again the symbol always represents the positive or the principal nth root. And then for the case with 0, then the nth root of 0 is always 0. Okay, notice in all these cases the index n has to be bigger than 1, and it could be even or odd, but it has to be bigger than 1. It has to be an integer. And it's important to kind of have certain roots memorized, because that will help you a lot when we do some problems, just so you don't have to use the calculator too much. So here's some numbers you try to memorize. Here are the perfect cubes. 1 cube is 1, 2 cubes is 8, 3 cubes is 27, 4 cubes is 64, 5 cubes is 125. So again, if you memorize some of these, that help to do it quicker. And then here's the fourth powers. 2 to the 4th power is 16, 3 to the 4th power is 81, 4 to the 4th power is 256, 5 to the 4th power is 625. And then 5th power, 2 to the 5th power is 32, 3 to the 5th power is 243, 4 to the 5th power is 1024, and then 5 to the 5th power is 3125. So maybe some of the bottom one, maybe some of these big ones, we don't have to really know, but definitely all the lower ones, you definitely want to know. Anything I think 125 or 256 or less, you definitely should know. So these up here you probably should know, because they come up a lot. Okay, how do I simplify this? Again, this is the same thing as before. This denotes the positive square root of 4, which is 2. Again, if it's the cube root, there's only one of them. So the cube root of 64 is 4. Again, if you memorize those numbers, you help to do this a little bit faster. The fifth root of negative 32 is negative 2, because negative 2 to the 5th power is negative 32. The fourth root of 81 is 3. The sixth root of 1 million is 10, because 10 to the 6th power is a million. And that's easier because when you raise 10 to a certain power, it's just the number of zeros. So that's how we can see that the sixth root of a million is 10. And because this is negative 100, you can't take the square root of negative 100. So there's no real square roots of negative 100. Same thing, there's no fourth root of negative 16. And again, if this is an even index, and this is a negative number inside the radical, then this expression is not a real number. Okay, so here's a summary. Well, this is what if you have you raise a number to an n power and then take the nth root? Well, it seems like that should cancel, but not always cancel. It doesn't always cancel perfectly. So if n is odd, then it will always perfectly cancel. The nth root of a to the n power is a. So if n is odd, but if n is even, a positive even number, then the nth root of a to the n is actually the absolute value of a. And let's see why we need the absolute value when n is even. Okay, so I think the best way to kind of see an example. So notice in the first example, the fourth root of something to the fourth of negative 3 to the 4th power Again, if I just cancel blindly, then I get -3, but that's actually not right. If n is even, then this will cancel, but you have to take the absolute value of the inside. Will give you a +3. So again, because n is even, when you take the absolute when you take the nth root of the nth power, then you need to absolute value the base here, which is +3. And the reason is because if I were to do this slowly, notice -3 to the 4th power will give you a positive number, and the nth root of any positive number, as we remember, is the principal root, so the answer would be positive. That's why we need to take the absolute value, because this negative base needs to be positive if we were to do this carefully. But in the case where the index is odd, we don't have to worry about that. Just cancel -3. No absolute value needed. So again, if you have a even index, then you can't cancel these. You have to make sure you take the absolute value. Same thing here, because these are even indices, 2 and a 2, so when we cancel, you have to have the absolute value. But for odd root and odd powers here, it can cancel without the absolute value. And then same thing here, y squared to the 2nd power, the square and the square root here will cancel. And then you need to take absolute value, but y squared is always positive anyway. So in this case, because this is a positive number regardless, you can remove the absolute value because it's not necessary. Okay, let's do an example. Suppose you have 2 boats that leave the dock at noon. So here's the dock here. This boat is going to go this way, which is due east, and then this boat is going to go north. And suppose both of them going to travel. Actually, no. Going north, this is going to travel at 6 miles per hour. Going east is going to travel 8 miles per hour. The question is that after 2 hours, how far are they apart? In other words, what's the distance between these 2 boats after 2 hours? Well, we have to figure out where they are after 2 hours. So if the one going north is going 6 miles per hour in 2 hours, it would have traversed 12 miles. So this is 12 miles. If this is going at 8 miles per hour in 2 hours, it will travel 16 miles. So that's A and B. That's the length of these 2. So now we gotta find this hypotenuse. So again, notice this is a right triangle, and so we gotta find this hypotenuse C. And so we remember that there's a Pythagorean theorem equation we learned from back in high school, where if you have a right triangle, a squared plus b squared is c squared. So that's the equation. So a is 12, we saw, b is 16. So if we square those and add them, we get 400, which is equal to c squared. And now we have to take the square root of both sides. And again, the square root here is the principal root, so which is root of 400 is 20. And the reason why we picked this principal root is because, well, this is distance, so it's always going to be positive. So this will be positive 20, even though there's actually 2 square root of 400. Positive 20 and negative 20, we only take the positive one in this case. So the boats are 20 miles apart after 2 hours. Okay, let's talk about radical function. So notice that every time we introduce a new notation, a new function, we can also introduce the function notation for it. So after having talked about nth root, we can have a function that is the nth root function called the radical function. And then there's some restriction here. If n is even, we saw that the x has to be non-negative. But if n is odd, then the domain is all real numbers. And so, for example, here's the function g of t, which is the 4th root of t minus 2. And because this index 4 is even, we have a restriction on what you're allowed to take, namely that you cannot take the 4th root of something negative. So you need to make sure that t minus 2 has to be non-negative. So that means t minus 2 has to be bigger than or equal to 0. Solving this inequality gives us that t has to be bigger than or equal to 2. That means the domain of this function, g of t can only allow to be 2 or bigger. So that means the domain of this is 2 to infinity, including 2. So that's how you find the domain of radical function, is to look at the index. If it's even, we have to make sure that whatever the expression is under the radical, in this case t minus 2, needs to be non-negative. But for odd radical, like the cube root, there's no restriction on a. We can have both positive and negative inside the radical. Therefore, the domain is all real numbers. And then I guess I forgot to have the slide for this the next problem. which is part C, but it's the same deal. In other words, and I'll put the slides in once I upload the slides to Blackboard. But 3 minus 5x, we need that to be non-negative because this is an even root, and then solving that inequality will give us the domain of this function. So again, I'll post that later. Okay, rational exponents, 6.2. Okay, what are rational exponents? Well, this basically we have an exponent that is a rational number. In other words, has a fractional part. So let's start with a simple example. If n is an integer, and a is a real number, and n again has to be bigger than 1. Again, because when you take the nth root, n has to be an integer that's bigger than 1. Then we're going to define. Here's the definition: a to the 1 over n. Again, if the exponent is 1 over n, then that's the same thing as the nth root of a. So, for example, negative 8 to the 1/3 means we need this to be the cube root of negative 8. And so the cube root of negative 8 is negative 2. So negative 8 to the 1/3 is negative 2. 1/4 means the fourth root of 81. So the fourth root of 81 is 3. Again, we want the positive principal root. And notice in this case, this is a little bit tricky. When you have a negative 100 to the 1/2, again, we cannot take the square root of a negative number. But notice in this case, it's actually by order of operation, PEMDAS, we have to do the exponent before we do the any multiplication. And so this nth root is actually only applying to 100. So you have to do the square root of 100 first, which is 10, and then multiply by negative 1. So this is negative 10. So again, this is not an error here. This is negative 10. But this is an error though. You cannot take the square root. Again, 1/2 means the square root. So you cannot take the square root of negative 100. Okay, so that's the case when the rational exponent is simple, like 1 over n. But whatever is more complicated, like the general case, which is m over n, which is the general rational number. And so this is we're going to use a property of exponents to do this. But the idea is that you have 16, for example, to the 3/4. There's two ways of doing it. One way is to take the 3 in the numerator outside of the exponent. Remember, when you raise a power, something to a power to another power, you multiply the exponent. So 3 times 1/4 is 3/4. So if I do it this way, then I get that we had to first take the fourth root of 16, which is 2, and then we cube it, which is 8. So that's one way of doing that. Another way of doing it is to kind of instead of taking the 1/4 to be inside and the 3 to be outside, we can also reverse that and say put the 3 inside and the 1/4 outside. So in that case, we do 16 cubed, which is 96. And then the fourth root, again, 1/4 is the fourth root of that is 8. And so we can do either way, but you can see from here that one way is much easier, and that is the top way. In other words, it's better to take the root first, then raise to a power, than to take a power first, then take the cube root. And the reason is because you see from this example that taking the cube root of a small number is much easier. Because if you cube it, if you raise it to the power first, then you gotta take a fourth root of a big number, which is a lot harder. So again, take the root first, which is a little bit, because this is a small number, and then raise to the power. That's easier. If you try to reverse that and try to raise to the power first, the answer will be a big number. Then trying to take the root of a big number might be a little bit trickier without the help of a calculator. So this allows us to give it this definition. When you have a number to a rational exponent, assuming that these are positive integers and that a is a real number, and assume that this is already simplified in lowest term. In other words, they share no common factors, and n has to be bigger than 1. Then when you have this rational exponent, there's two ways of doing it, as we saw in this example. One way is to take the nth root, so m over n. So the denominator is always the root. The numerator is always the power. So one way is to take the root first, the nth root, then raise to the m power, which is in this case the nth root, then the m power. Or another way of doing it is to raise to the m power, then take the nth root. Either way will be the same answer, but as we saw earlier here, it's better to take the nth root first when it's small, and then take the power later. So that's the way we recommend to evaluate these rational exponents. So let's see some example. So 8 to 2/3, again, the 3 is the cube root, the 2 is the power, so let's take the cube root first. The cube root of 8 is 2, 2 to the second power is 4. And then 5 over 2 means that, again, take the root first. Square root of 100 is 10, 10 to the fifth power is 100,000. And similarly here, 3/2 means that you take the square root and then raise to the third power. Square root of 1 over 25 is 1/5. Raised to the third power is 1 over 125. So again, notice that the root here is always the principal root. And finally, when you have something negative, one way to do this with using the law of exponents is to you can bring in the negative. You can make it positive by flipping the base. In other words, if this is a 4, to make this a positive 3/2, you flip the 4 to be 1/4, and then you distribute this power to each of the term. 1 to the 3/2 is the same thing as 1. 4 to the 3/2 is where you do the square root and then the cube power. So the square root of 4 is 2. 2 cubed is 8. So you have 1 over 8. So you got to do it so carefully. And finally, again, if you notice that the 4 here is a fourth root, which is even, so you cannot take the even root of a negative number. So this is not a real number. Okay, let's convert these expressions to radical notation. We're going to assume that all these variables are positive real numbers, so that there's no problem with taking a root of an even root of a negative number. So what does that mean? You have the a to the 3/5. So again, the 5 is a root, 3 is a power. So you can write this as so actually two ways of doing it. One way is to take the 5th root of a and then raise to the third power, or raise a to the third power and then take the 5th root. And then for this case, it's the same, except that now maybe we can try to do some factoring here. Notice there's a 1/3 power here and also 1/3 here. So factor that out of the expression as a power, so that now you have 5x squared to the 1/3. Again, you multiply this back in, you can check that it's the same. 1/3 times 1 is 1/3. 1/3 times 2 is 2/3. And so now we have the cube root of 5x squared. So again, when we try to convert these to radical notation, the idea is that we try to take the root, this third, the 3 root here, the third root, cube root, take that out of everything by factoring it out. And then anything to the 4th root is just to the 1/4 is the 4th root. So that's, I notice 3 here is not, this 4th root only applies to the y, not to the 3. And as I said before, if you have a negative exponent, you can always flip it. So 1 over this. And then the 4th root of z cubed. Okay, and then let's convert each of the expression to the rational exponents. So again, when you convert to the rational exponents, the root is always in the denominator, the power is always the numerator. So this is going to be 3 over 4. 3 is the power is the numerator, the root is the denominator. And this one is the square root, the same thing as raised to the 1/2. This root only applies to a, so only a is raised to the 1/2. Okay, that's actually very helpful to remember that the square root of something is the same thing raised to the 1/2. Okay, so some of these is review of laws of exponents, properties of exponents that might be helpful when we work with rational exponents. And we saw some of this previously, but let's review here. So when you multiply two things on the same base, you add the exponent. When you divide things on the same base, you subtract the exponent. A to the m to the n power is a to the mn. Notice we just multiply these. And then when you raise a product of something to an n power, you can distribute the exponent to each of the terms. Same thing with division. This power goes to both the a and the b. And then as we saw earlier, when you have negative exponent, we can make it positive by flipping the base to be 1 over a, for example. And then anything to the 0 power is 1. Okay, so let's use properties of exponents to simplify these rational expressions that involve rational exponents. So again, assuming that all variables are positive, so that we don't have any problem with even root of negative numbers. And so same base here, so we add the exponents. So 2/5 plus 3/5 is 5 over 5, which is 1. And then notice when we divide, we subtract the exponents. So negative 1/2 minus 3/2 is negative 2. And so if this is a negative power, you can flip it. So 6 over a squared. And then when you have the whole expression raised to an m power means that that power is applied to each of the terms inside the expression. And so, and the way it works is that you multiply these, right? 4 times 1/2, and then 4 times 1/3, so that's over there. 4 times 3/4, so you multiply that. 4 times 1/2 is 2. 4 times 1/3 is 4/3. 4 times 3/4 is 3. Okay, that's the end. Thanks for watching.